PolyU is ranked the second best university for civil engineering and ranked fourth worldwide in the display of civil and structural engineering in the QS World University rankings by subjects. We have performed particularly well in securing external research grants, including 4 theme-based research projects obtained by Professor Ni, Professor Li, Professor Teng, and Professor Wang. We also did a good job in obtaining the Green Tech Funds and RGC Collaborative Research Funds and RGC Research Impact Fund. Throughout the years, our departments developed close collaborations with the local construction industry, overseas institutions, and partners in a wide range of research projects. The department offers a wide range of programs in civil and environmental engineering fields, like the undergraduate program, civil engineering and environmental engineering and sustainable development. We also provide the postgraduate programs, like the Master of Science in Civil Engineering and Master of Science in Environmental Management and Engineering. Besides, the research postgraduate programs are also offered in our department, like the MPhil and the PhD. Here are our outstanding alumni and our facilities. Currently, there are 30 laboratories, 2 workshops, and 1 research center in Shenzhen. And you can get more information. You can get more information from our department websites and see newsletters. And you can also scan the following QR code to get more information about our department. Now let's move into today's topic. The title is Image-Based Characterization and Discrete Element Modeling of Grain Materials. That's the outline. The first part is background of research. We will talk about the nano-focus accuracy work from 2 aspects. One is particle morphology characterization. Another is soil properties investigation by using the operators combined with the accuracy T. After that, the DM modeling of soil behaviors will be introduced, like the one-to-one DM modeling and irregularly shaped particle bricks analysis. The last part is machining applications to materials. We can use this method to track the particles and also to predict the soil mechanical behavior. As you know that the grain materials are the foundation of geotechnical engineering, are closely related to several natural hazards, like the landslides and liquefaction. And this kind of materials normally exhibits complex mechanical behavior, which is mainly caused by the particle size, particle shape, and mineralogy. And this grain materials normally shows nonlinear behaviors, like the dilation or contraction during shearing. So the purpose of this study is to help us to better understand the mechanical behavior of soils by using the accuracy T, DM modeling, and the machine learning method. Now let's move into the first part of the research work, nano-focus accuracy work. And we can, as well know that we can use the accuracy T to get the particle shape and also its microstructure. And this figure shows the silica sands. And we can see that compared to the silica sand, the surface of decomposed granite is more rough. And the below part is for the carbonated sand particles. And by using the accuracy T, we can get its internal voids and the initial macro cracks. And But we need to see that by only using the accuracy to get the particle shape is not enough for us to analyze the soil mechanics. So we need to develop a set of operators which can be used combined with the accuracy to analyze the mechanical behavior of soils. So in our research group, many loading operators were designed by Dr. Zhao to perform the single particle crashing tests on natural sand particles. A three-dimensional scheme and a photograph of the operators are illustrated in this figure. And this device consists of three major parts: the sample chamber, the loading and data acquisition system, and the primary frame. This test was conducted in a laboratory CT scanning system located at Shanghai Yinhua Company. And in this study, two types of natural sand particles with different morphology, mineralogy, and microstructures were tested. Considering the load capacity of the operators and the resolution of the CT scanning, particles with the dimensions between 1.2 and 2.0 millimeter were used herein. And each sample was scanned by rotating the apparatus 360 degrees around its central axis between an accurate tube and a detector. After the scanning test, a series of radiographs of the sample were acquired. And we will use after the scanning test, a set of image processing techniques will be used herein to process the obtained images. And for instance, the three-dimensional media filter was used herein to reduce the noise in the raw images. And the histogram of the grid level distributions before and after using the three-dimensional media filter is illustrated in Figure C, from which we can see that the intra-class variance were reduced after using the filter. And the thresholding algorithm will be used herein to segment the images based on the threshold found on the Figure C. And because we are only interested in the grain, which is the only materials kept in the image, where the silicon grains and voids will be removed after the thresholding algorithm. So after that, the watershed algorithm will be used herein to detect the context particles and to separate them from each other. And we will use different color to describe their fragments. And that's the reconstructed results for the crust sand particles. And that's the LBS sand particle and its E sand particle. And this work was conducted by Dr. Zhao. And by using the single particle crashing text, we can get the relationship between the force and displacement. And we can also get the crust sand particles after the text. So that's the video to show the crust sand particles. And because in situ CT scanning was used herein to scan the crust sand particles, so that means we can observe the whole particle breakage process. This line shows the initial state before the crashing text. And this line shows the crust sand particles. And we can see with the increase of the acute strain, the particle will crash into numerous fragments. And herein we will use the particle shape parameters to describe the evolutions of the particle shape, like the sphericity and convexity and aspiration. Now, if we have now let's move into the image matching part. If we have this kind of data, how can we analyze the particle frequency deeply? So here is the question: how can we identify and track fragments if we have the crust set particles in this data? Now we will use two-dimensional image matching work as an example to illustrate the whole process. And we can see there is a fragment and a template. So the first step is to find the key points from its boundary. So from the key points, we will make a comparison for the key points from the template and fragments. So we will get the corresponding points. After that, we can get the translation and the rotation between them. So we can match them together. And we will call this method as fracture region matching. Now let's see the three-dimensional fracture region matching. Herein, we can extract the boundary of fragments based on the curvature. After that, we will use the 4PCS method to help us to get the key points from its boundary. The first step for this method is to find the 3 points from its boundary. And because the 3 points can determine a plane, so in this plane, we will find the 4th points. So these 4 points will be considered as the key points. So we repeat this process, we can get a series of key points. Now we will make a comparison between the key points from different fragments. Now we can get the corresponding points. Here we use a line to connect them. And the singular value decomposition will be used here to help us to get the translation and the rotation, this relationship between two different fragments. And the matching results will be evaluated by using the ring triangle intersection algorithm. And now the following are the matching results. And this method actually is conducted on 4 alveolar sand particles. Here we only illustrate 2 alveolar sand particles. And here is alveolus 2 sand particles, which is crushed into 4 large pieces and numerous small fragments. And we can see that the volume of the reassembled alveolus 2 is about 98% of the original volume. And another one is alveolus 1 sand particles, and this particle will crushed into more than 10 fragments. But we can still get a good matching results here, demonstrating the effectiveness of the proposed method. Now let's see the second phase of image matching work. Because the first phase is very time consuming, because we need to conduct the image matching work between different fragments. The second image matching work was conducted between the child particle and the mother particle. We will call the fragment as the child particle, and we call the initial original sand particle as the mother particle. So the first step is to segment the child particle into several phases. Now we use different color to describe the phase. And the iterative close point algorithm was used here to perform the registration of point cloud data between segmented phases and mother particle surface. Because the right matching always has a smaller distance error compared with the wrong matches. Based on this criteria, we can always find the right matching out. So that's the basic solve. So here is the matching results. The blue one is the surface of the mother particle, and the original one is the phase from the fragments. And this animation is used here to illustrate the whole matching process. And the charged particles were reassembled together to obtain the overall matching results. And the green color represents the mother particle surface, and the green color represents the original physics of a charged particle. And we can see that because this area will have a high point density compared with the other areas. Based on this, we can extract this area out, and we will call it as original surface for the charged particle. And the rest of surface will be regarded as the fractal surface. And this information can be used into the DM modeling to help us to investigate the effect of intrinsic flows on the particle breakage, and we will talk about it later. And but the second method is very susceptible to the local minimal problems. And this method has a limitation that requires that the charged particles must be distributed very close to the original location of the mother particle from the in situ CT scanning experiments. So here to overcome this limitation, we have use the global RSP algorithm. That's the basic thought. We can assume that there is a such space expressed by the cube. And the purpose of this study is to find the right points in an efficient way. So the first step is to divide the initial cube into 8 subcubes. And we will to calculate the up and lower bounds for each subcube. And those cubes whose bounds exceed the threshold value will be discarded, and the remaining subcubes will be explored by calling the standard RSP algorithm to update the data error calculation file by the CIDR. So the typical convergence curves of the lower bounds and up bounds are illustrated in this figure. And we can see that the up bounds and lower bounds decreases and increases respectively, approaching to each other quickly. And the data error tends to stabilize at around 0.6 after about 5,000 seconds. And for this figure, we can see the blue points stand for the mother particle surface, and the origin points stand for the charged particle original surface. And we can see, although the location of the charged particle surface is not close to the original location of the mother particle, but the used algorithm can still help us to identify the original location of the charged particle, demonstrating the effectiveness of the used algorithm. So in addition to the above work is for the single particle crashing text. And in addition to the single particle crashing operators, a mini triaxial operators were also developed in our research group. This device was designed by Dr. Chen, and I will introduce a little bit about this device. And the loading system can provide a maximum axial force of up to 5 kN, which is achieved by a servo-controlled step motor. For the confining pressure offering system, the GDS pressure controller is adopted to provide a constant pressure to compress the sample within the chamber through water. And a maximum confining pressure of up to 2,000 kilopascal can be applied. The height and the diameter of the sample tested are 8 and 16 millimeters respectively. It shall be noted that the use of small sample size is primarily motivated by the requirement of the rotation table and the need to obtain high resolution cross-sectional CT images for investigating the grain scale mechanics. Considering the weight and the height of the design apparatus, the CT with an accurate source energy of 25 kilovolts and a rapid scanning set up at Shanghai Synchrotron facility was selected to investigate the deformation behavior of a soil sample. The spatial resolution of the detector is 6.5 micrometer, and its scanning window size is 4.8 millimeter in height and 12.6 millimeter in width. Now, we will use these apparatus to investigate the particle breakage in sand and trash sharing. And the soils used in the in situ CT tracer test were sampled from the Honghe River Yunnan province. And this sample was mainly composed of two types of natural sands, namely quartz and calcite, with grain diameters varying between 0.2 millimeter and 1.5 millimeter. As we all know that the quartz sand particles have a relatively high degree of roughness and a smooth surface, and are chemically stable with a high crashing strength. And the calcite grains have more irregular particle shapes and a lower crashing strength, so which is favorable for the particle breakage analysis. The confining pressure of 2000 kilopascal is used herein to compress the sample. And the stress strain curve and the volumetric response are illustrated herein, in which the red circles indicate the 6 scanning points. And this figure also shows the volume rendering of the CT images at the 6 scanning points to illustrate the soil deformation process. A typical example of the cross sections of the sand grains at the 6 scanning points is illustrated, from which we can see that several irregular shaped particles were crushed into a certain number of small fragments, indicating that the degree of particle breakage increases with the increase of the axial strain. And the proposed image matching techniques were used herein to help us to divide the sample into two groups, uncrushed sand particles and crushed sand particles. All the particles expressing a 0 or slight degree of particle breakage will be regarded as the uncrushed sand particles, and the rest of particles will be regarded as the crushed sand particles. And in this study, more than 5,000 times of trial matching were made. It takes about 5 days. And it will be easy for us to get the number of particles for each group. And like we can see for the tracked sand particles, the number of particles increased from 0 to decreased from 512 to about 150, and the number of untracked particles increased from 0 to about 2,700. So we can see that the rate of the decrease of the former curve is much lower than the rate of the increase of the later curve, indicating that the average degree of particle breakage rises rapidly, perhaps with the particle crashing mode evolving from the tripping or sliding at the pre-peak stage to comminution at the post-peak stage. And we can also find that half of initial particles were crushed before the peak stress was reached, and the green breakage started to accelerate very early around the yielding point, but slowed down after 63 points and continues with a constant rate until the end of the text. Following the single particle crossing text, here we can also use the particle shape parameters to describe the evolution of the particle shape. And the particle shape parameters are the sphericity, convexity, flatness, and elongation. And we can see that for the sphericity and convexity, these particle shape parameters increase with the increasing axial strain. And a similar trend also holds for flatness and elongation, although it's less pronounced. So we can see that all the particles that are crossed tend to have a lower value of particle shape parameters. And this result is well expected because particles with a higher degree of angularity and irregularity are more likely to crash. Here we also calculate the distributions of the particle size. And it's a common sense that the large grains have a lower probability of survival due to the possible existence of a large number of intrinsic flaws. And by observing this figure, we can see that the number of newly generated fragments from the particle breakage increases rapidly with the decrease of their particle size, especially when particle size is smaller than 0.6 millimeter. So this result indicated that particle crossing mode involves from the tripping or splitting at the pre-peak stage to comminution at the post-peak stage. So the above work is from the mini operators which can be used with accuracy T. Now the following part I will introduce the DM modeling work. And the first work, and because from the previous work we can use the accuracy T to get the particle shape. And we can also use the image matching techniques to help us to get the fresh surface and original surface. And now we can put this, now this information can be imported into the demonstrations to help us to analyze the particle breakage deeply. Now we can, this geometry is the particle shape. And we can see within this geometry, there is the intrinsic flows obtained by the image matching work. And the blue color represents the contact network. And the red one is the intrinsic flows. And we can randomly select a part of connex intersected by the realistic fresh surface, and setting the intrinsic flows by lowering the polar bond strength. So now we can analyze the effect of intrinsic flows on the particle breakage, like the relationship between the force and displacement, and also particle crossing mode. And we find that the number of initial flows plays a more dominating role than the reduction factor of the bond strength in reproducing the real particle crossing behavior. And the initial flows have a relatively slight influence on the stiffness behavior, but affect the particle crossing strength significantly. And the particle crossing behavior, like the peak crossing load, flex pattern, and the configuration of the fragment is subject to the combined effects of the particle shape, particle morphology features, and initial flows. And this method we use the cluster with we use the boundary sphere to describe the particle shape. And another part is we can use the clump to express the irregular particle shape. And the clump is controlled by two parameters. one is rho, another is phi. And we find that when the rho is equal to 0.3 and phi is equal to 150 degrees, the reconstructed clump can reprint the particle morphology very well by checking the volume of the reconstructed particle. Herein, we use the one-to-one mapping techniques to build the DM model. And the one-to-one mapping means every sand particle in the experiment also has its numerical twin in the DM simulations. And the flex membrane composed by boundary spheres were used herein to provide a constant pressure and also to reflect the deformation behavior of soils. Because in the previous study, they normally use the rigid walls to provide the pressure, but it's hard for this method to reflect the deformation of soils during shearing. So here we use the boundary sphere to reflect to make up the flex membrane. And the following are the DM simulation results. And this figure shows the deviatoric stress and volumetric strain. And the confining pressure was tracked using a measurement sphere to ensure that the confining pressure was applied correctly. And we can see that the membrane performs very well to apply a constant confining pressure of 1.5 MPa throughout the shearing process. And for the deviatoric stress and the volumetric strain, we can see there is a good agreement at the microscopic level between the experiment and the DM simulation. For the DM simulations, for the deviatoric stress, we can see in the small strain level, the agreement is almost perfect, indicating that the complex contact interactions and stiffness, which are mainly controlled by the irregularity of particle surfaces, are well reproduced. And this figure shows three-dimensional polar distributions of the branch vector orientation from the simulation and experiments. And the branch vector is used to identify and define the contact of two adjacent particles, although these two adjacent particles may have more than one contact. And we can see overall, there is a good agreement between the interparticle and interclump distributions from the experiments and the simulation, respectively. In addition to the microscopic level, we also do the analysis at the particle scale, at the particle levels, like the particle kinematics. To further demonstrate the simulation results, we calculated and plot the cumulative distribution of the particle displacement and rotation. And we can see for the particle kinematics, there is also a good agreement between the simulation and the experiments. The last part is related to the shear strain and volumetric strain. And this figure was obtained by Dr. Chen, actually, and this figure was not, and which is not included in the published paper, because the reviewer think the results is not very good because and we can see the surface of the shear strain from the experiment is not very smooth due to the limited number of the tracked particles. Apart from this, we can still capture the incline bands within the shared sample by using this method, actually. So the above results demonstrating the effectiveness of the proposed one-to-one mapping techniques. And based on the one-to-one mapping technique, we can do so many things actually. Like we can simulate the rock-shaped particle breakages, and we can analyze the mechanical behavior of soil and rock mixture. Actually, we can also propose several algorithms like to investigate the particle kinematics and also to describe the evolutions of the context during sharing. Actually, this work was mainly conducted by Dr. Chen. My work is focused on the DM simulations. And here now we already introduced, we can use the clump or the cluster to describe the particle shape. Here we will use the rigid block, another way to describe the particle shape. And FDM-DM method we use here to replicate the accuracy-based experimental results and to simulate the particle breakages. And unlike previous study that employed the clump or cluster to represent the particle shape, here we adopt the rigid blocks for modeling the particle geometries. And we used the particle replacement method to simulate the particle breakages. 5 chart particle templates were generated based on the CT scanning results. And each template selected to generate the chart particles were based on the current value of the actual strain. To reflect the deformation behavior of the sample, we introduced the use of a flex membrane using the FDM to enclose the sample. And this this DM solutions it's executed through 3D algorithms. And the primary algorithm, we will call it as algorithm 1, manages the 3-dimensional sharing text and checks for particle breakage every 100 time steps based on a given particle breakage criteria. And where a particle meets this criterion, it's labeled for crossing in the next step. And algorithm 2, they select the true fragment templates for fragmentation, which is constructed based on the CT scanning results that have detailed both crossed and uncrossed particles using the proposed 2-step particle tracking method. And following this, algorithm 3 takes over to replace the selected particles. So we can repeat the process to simulate the particle breakages. And that's the simulation results. And this figure shows the special distributions of cross-section particles within a sample, segmented into 2 straight intervals marked in orange and blue respectively. And know that the size of each sphere represents the density of points around it. Larger spheres indicate a high local density of the particles. So we can see that in the 0 to 6% strain range, the particle breakage is uniformly distributed throughout the sample. As the strain increases to between 6% and 50%, the particle fragmentation becomes more concentrated near areas of stress concentration, particularly around the incline bands. This shift indicated that as the material is subjected to a high stress, the stress distributions becomes more localized, focus on areas that are weak or more prone to failure. Actually, we also illustrated the relationship between the contact fault chains deformed area and fragments within granular materials. And we can observe that the distribution of this force correlates with the appearance of the inclined bands, where material deformation is concentrated, typically lying along the maximum shear area within a sample. And these areas with large surface also show significant particle breakages. And actually, the above work is for the DM solutions, because we proposed one-to-one mapping technique. Following this, we can conduct parametric study to generate a large database, for machine learning this method. And the first work is to use the machine learning this method to track the carbonated sand particles, because in addition to the image matching work, we also used the machine learning this method, to track the porous sand particles. And because compared to the alveolar sand particles, the carbonated sand particles have rough and concave surfaces and abundant intraparticle pores, so which makes them high crushable. Besides, it commonly has irregular particle shapes. Due to these features, over-segmentation or less segmentation may be occurred during image processing techniques. So before tracking sand particles, a modified image processing techniques were used herein. The basic idea of this method is to perform the hole filling and closing operations to generate water pixels and to fill these intraparticle pores. After that, the generated pixels will be deleted to restore the surface after implementing the water share algorithm. Another challenge for this method is for this study is that the current city data is insufficient for training and testing the neural network. To overcome this problem, a strategy of sampling and grouping were proposed. The main idea of this method is to divide the initial point set of each carbonated sand particles into several groups using the farthest point sampling. To evaluate the difference between the generated point sets, particle matching technique was used herein. Because a special resolution of 5.0 micrometer was used here to scan the carbonated sand particles. So that means the particle surface was composed of millions of points, which is enough for us to perform the sampling and grouping strategy. And this yellow figure shows the matching results, and we can see that along the diagonal, the data errors are all equal to 0, indicating that the matching between the two same point sets is perfect. However, apart from these areas, there are some differences in the distributions of the two different point sets, but a high similarity of the point structure exists between them. Therefore, we can believe that the point set generated can serve as a faithful representation of the original particle and are suitable for this deep learning exercise. and that's the PolyNet neural network, and we use this network to capture the local and global the combined features of carbon dioxide particle from the local and global levels, and to track the carbon dioxide particles within assembly. And in this study, 67 carbon dioxide particles were used here, to validate the constructed neural network. And this figure shows the tracking results, and we can see that the constructed neural network has achieved outstanding performance in tracking the carbon dioxide particles. With only 1 vote, the prediction accuracy is 1 for all particles except the particle with the RD 18, which has an accuracy of 0.8. And when the number of votes increased to 3, all the particles are successfully tracked with an accuracy of 1. This result demonstrates again the high capacity of the designed PolyNet neural network on the tracking of the porous carbon nanosites. So this work is using the neural network. Using the neural network to help us to track the carbon dioxide particles, and we can also we all know that we can also use the neural network to predict the mechanical behavior of soils. Here we construct the artificial neural network to predict the 3-dimensional contact forces. The basic idea of this method to predict the contact forces is to capture the evolution of the contact force in its direction. Because contact force orientations can be decretized into several equally spaced patches and characterized by a 3-dimensional Ross histogram. So it will be easy for us to predict the contact force in each patch. Because in the previous work, we built a DM model which can be used to reproduce the experimental results. Now, based on this model, we also use the 3-dimensional particle flow code to perform the triaxial sharing test simulation to create a big database for machine learning analysis. Before constructing the artificial neural network model, the input and output data are normalized to ensure the computational efficiency. And here a total number of 10 features, including 5 particle scale features and 5 measure scale features, were selected for the establishment of the artificial neural network. The features are coordinate number, particle size, and displacements in X, Y, and Z directions. Here we show the distributions of the correlation coefficients. We also plot the distributions of the R and we also validate the relationship between the correlation coefficient and the local porosity. The dense and loose samples were considered here, and that's the prediction results. And a comparison between the predicted 3-dimensional orientational distributions of the contact forces and the ground truth at actual strain of 0% and 50% were made for both dense and loose samples. And we can see that the predicted contact fault trains are in good agreement with the ground truth during the whole sharing test for both loose and dense samples. And this excellent overall agreement suggests that the proposed artificial neural network is capable of accurately predicting the entropy of the contact fault trains in a shared granular materials and highlights the significant contribution of this study. And the last one is we use the machine learning this method to help us to capture the constitutive behavior of soils during sharing. Actually, so many people did similar work actually like this one. It's a common one. And here a total of 300 DM simulations were conducted here with the different initial processes from the 0.4 to 0.6 to reflect the relative density of the initial sample. And here is the video to show the how can we create the large database to generate the database for the machine learning this method. And this code was developed by Dr. Liu actually help us to generate the database. And here we use the LSTM model to capture the constitutive behavior of soils. And the input data are the initial wall ratio, confinement pressure, and initial particle sharing parameters to predict the mechanical behavior of soils. And this figure shows the distributions of the loss value for the training and texting datasets. And that's the prediction results. Like the stress ratio. Actually, we make a conversion between the experiment and between the experiment simulation and also the prediction from the neural network. And we also predict the evolution of the wall ratio and the entropy of the contact fault trains. And also the entropy of the fabric. Now let's move into the conclusion. Now we will summarize the previous work. And from today's topic, we know that the nanofocus accuracy work is a powerful tool for the realization and calculation of standard particle morphology and microstructure. And we also proposed 3 phases of image matching techniques. The first phase is performing the image matching between the fragments, and the second phase is conducting the image matching between the child particle and the mother particle. The last one, we improve this method which can be used in a granular assembly. We also proposed the one-to-one mapping technique. Actually, this technique is very similar to the digital twin, actually. So, and the proposed one-to-one mapping technique, can help us to reproduce the stress strain response and volumetric response with a very high accuracy. Based on the constructed DM model, we also built a simulation framework to simulate the irregular shaped particle breakages. The last one is about the machine learning this method. And actually, we can use machine learning method so to do so many things on the image processing techniques and or using this method to capture the soil behavior during sharing. So here is the acknowledgements, and thank you for your time.
Thank you, Dr. Wu, for your presentation. So if you have any questions, please feel free to raise the questions in the Q&A box. It seems there are no questions from the audience. Okay, so thank you, Dr. Wu, for your presentation, and this is the end of today's webinar. Thank you all, and bye-bye.
Okay, thank you. Okay, bye-bye.